There we go. All right, how's everybody feeling? Second to last week before the end of the semester, exam week. Yep, almost over the final hurdle. Oh, just realized my camera's still off. There we go. All right, I'll get right into it, and there's just a little bit more I wanted to cover before we finish this chapter, and then that's going to be sort of the point where for the exam, at which time I'll pause for you to ask any questions about the exam that you'd like before continuing on to spectroscopy. So just some quick recap. In this chapter, we were trying to figure out how to deal with this thing called spin, electron spin. What we said is we can take the wave function and we can multiply it by some spin function we call either alpha or beta.
Minute. I gotta go get blood work.
Hang on, gotta mute yourself.
I don't hate anything.
There we go. All right, just remember to mute yourselves on entrance, right? Disturbs everyone else. Okay, alpha and beta, right? So we don't know what they look like. We just know we're going to multiply our wave function by some spin alpha and beta. By the way, I don't think I mentioned this first time around, but alpha and beta. So if you integrate alpha and beta, and I'm using the Dirac notation here, if you integrate alpha and beta together like that, you get 0, meaning that they're orthogonal. Right? All wave functions, if they're not the same wave function, they should be orthogonal. And we've learned about this before. All right. Then we try to put this together for a helium atom. And we learned that the wave function must be antisymmetric with exchange to fermions or electrons. This is the Pauli principle. So we talked about the Pauli principle. And with the Pauli principle, we figured out that the wave function for helium should look something like this: 1 over square root of 2 times the 1s for the first electron times the alpha for the first electron, 1s for the second electron times beta for the second electron, minus 1s for the first electron times beta for the first electron, and 1s for the second electron times alpha for the second electron. And we talked about how any wave function for more than one electron would be sort of this term right here, a Slater determinant multiplied by 1 over square root of n factorial times the Slater determinant terms, which we showed how to make those up. So that's for any wave function for more than one electron. We do that because the wave function needs to be antisymmetric. And then one of the things that we talked about before we wrapped up last week are different types of calculation. We talked about Hartree-Fock had no electron correlation, right? An electron correlation is basically just interactions of electrons with each other, sort of. We said one level up from that are these MPX that has some electron correlation. I'll just put it like that. Above that, there's CCSD stuff that has more electron correlation. And then finally, there's FCI that has all the electron correlation. So if you see methods like that, you know what they mean. And when we write methods for computation, there's usually the method slash and the basis set. So it's method slash basis set. I'm showing you this so that if you see them somewhere else, you are able to recognize what's going on. And that's sort of where we left off last time, right? We talked about how do we write a wave function for multiple electrons and how we solve this using computational methods. Today, I want to continue this to talk about how do we understand what these orbitals look like in systems with more than one electron. And to do that, we're going to look at a method, or well, I'll title this one, Understanding Molecular Orbitals And we're going to try to understand them using something called a linear combination of atomic orbitals, or LCAOS. So we know what atomic orbitals look like. Let's talk about what atomic orbitals are first. Atomic orbitals sometimes are AOs for short. They're 1 electron or 2 electron wave functions associated with a single atom. And we know what these are because we've been looking at them for a while now. They're, for example, the 1s orbital, the 2s orbital, the 2p orbital, 3s orbital, and so on. Those are atomic orbitals. We know exactly what they look like. We've been staring at them for many, many years now. Molecular orbitals, on the other hand, so molecular orbitals, or MOs, are 1 electron or 2 electron. I say 1 electron or 2 electron because typically up to 2 electrons could fit in a same orbital with the different spins, right? So molecular orbital are either 1 electron or 2 electron wave functions that span the entire molecule. Meaning they're just not associated with one atom or the other. Similar to like atomic orbitals though, electrons must fill molecular orbitals following the Aufbau principle, meaning we fill from lowest energy first, and also using Hund's rule, meaning that if they're degenerate orbitals, we fill them with 1 electron first before coming back to fill them with more electrons. So that's the difference between atomic orbitals and molecular orbitals. Now, we know what the atomic orbitals are and what they look like. They're the 1s, 2s, and so on. And we've seen what those look like. But then the question becomes, what are molecular orbitals? What do they look like? So we're going to take a look at that specifically. But before we do, there's 2 more terms that I wanted to introduce to you. The first is the highest occupied molecular orbital, or HOMO, right? And this is the molecular orbital of the highest energy that has an electron in it. And similarly, there is a lowest unoccupied molecular orbital. These are just some definitions that we're going to see play out next. So the lowest unoccupied molecular orbital, or LUMO, and this is the molecular orbital of the lowest energy that does not have an electron. So this is quite a few definitions of stuff, and we're going to put this all together, and we're going to see what they actually mean. Am I frozen? Can you guys hear me? Hello?
Yeah, we can hear you.
Is my screen frozen? Because my screen just got frozen.
No.
All right, I just draw a little squiggly thing. Can you see that?
Yeah.
Ha. All right. Well, my computer's frozen, even though you guys can see things. So I'm gonna have to restart. I'm sorry. Give me 2 seconds. I'll restart. I'll be right back. Sounds good? Sorry about that. All right, I am back. Didn't take too long. Sorry about that. Oh, of course, my laptop screen isn't working now. That tends to happen from time to time. I have no idea why. All right, so we're talking about atomic orbitals, molecular orbitals, and how there's some highest energy orbitals with electrons in it. That's the HOMO. And then there's some lowest energy orbital without electrons in it, and that's the LUMO. But graphically, let me show you what this is. So let's say we're going to draw energy on the y-axis like this. And these little lines are going to represent different molecular orbitals. Just, I don't know. And let's say some of these will have electrons in them. Remember, when they get filled with electrons, the Aufbau principle says we have to fill from lowest energy first. So maybe those are all filled, and then the others on top are not filled, right? We say that these are occupied, right? Because they have electrons in them. And these are unoccupied. Some people use the word virtual because there are no electrons in them. So they're unoccupied or virtual. This orbital right here, right? It's the highest energy orbital that has electrons in it. So this will be the HOMO. And this orbital right here, it's the lowest energy orbital without electrons in it. That's the LUMO. And typically, it's important for us to identify what these are, because that energy difference between the HOMO and the LUMO, right? That can tell us about if we were to add energy to this electron, that's probably the most likely place it's going to go. So understanding HOMO, LUMO orbitals and their energy differences and stuff like that can be important for spectroscopy. Sounds good? All right. So I started this all by saying, well, what do molecular orbitals look like? Because we know what atomic orbitals, 1s, 2s, and so on look like. And to do that, we're going to use this linear combination of atomic orbitals just by assuming what would happen when we put two atoms together or two atomic orbitals together. So let's say you have an atom here, that's the nucleus, and an atom over here, and they both have, I don't know, a 1s electron, right? We know a 1s orbital looks like a sphere, so that's my 1s electron, right? What happens when they come together? Well, we know that when you add waves together, there are two ways to this. We could add those waves or subtract those waves. So if we add these waves together, what do we get? Here are my two nuclei. They both have the same sign. And for all of these drawings, I'm going to use orange to mean maybe a positive wave function, and I don't know, this blue to mean a negative wave function, right? So we have two positive wave functions and we want to add them together. All we're going to get is a bigger positive wave function. So on the left here, we're going to look at atomic orbitals, and on the right here, we're going to add them together to get molecular orbitals, because the wave function now span the whole molecule. And we need to label these. So on the left, these were called 1s orbital, or in fact, let's just make it general. Let's make it any s orbital, because they all pretty much look very similar. When they come together to form this big molecular orbital, we need to give that a name, right? So we'll give that a name sigma. This has nothing to do with sigma for spin. It's just that we run out of Greek letters to name things. Sigma just is a Greek letter for S. That's why we use it for spin, or in this case, the s orbitals when they combine. But there are other ways to combine these orbitals. For example, that's my nucleus. That's my nucleus. That's my 1s wave function. That's my 1s wave function. We know that you could also combine orbitals by subtracting them, right? So here's my s orbital and my s orbital. When you subtract these two, what do you get? Well, if you subtract them exactly in the middle where they overlap, they'll cancel each other out. But there'll be a little bit left over sort of over here on the far left that doesn't get canceled out. And on the far right, there'll be a little bit left over that doesn't get canceled out either, but it'll be a different sign because there's a negative sign here in front of that wave function. So this will be negative. We can't really call this a sigma anymore. So what we'll call this is sigma star, like that. Now, if we examine these, the one on top looks like it's holding those two atoms together, like it's forming a bond. So we'll call this a bonding orbital, right? However, the one on the bottom, exactly in between the bonds of the two nuclei, there is no there's nothing there. There's no wave functions trying to hold those. So we actually call this antibonding orbital. And I want to pause here and just ask a question. I know I did a little bit of this in Gen Chem. How many people are familiar with this? A little bit? Do you want me to keep going with the others, or? Yeah, okay. So all of the s orbitals can come together in this way. And so now we have a picture of what the molecular orbitals could look like. There's a bonding sigma molecular orbital that looks like this, or an anti-bonding one that looks like this little separation here. We can do the same thing for p orbitals. So let's draw my two nuclei, one here, one here. And there are different ways to draw p orbitals, right? So let me create some space all the way over here. Yeah. So here, this is our px orbital, positive and negative, right? That's px. A py orbital could look something like this. and a pz orbital. This one's hard to draw because it's in and out of the page. So let's say that's coming out of the page, and this is going into the page, kind of like that. I don't know. That's a pz orbital, right? That's the z orbital axis. This is the y axis. And this is the x axis. So there are three types of p orbitals that can come together to form molecular orbitals. And therefore, we need to think about each of these separately. So first, let's do the py orbital and see how they can come together. And then we'll move on to the others. So we're going to draw two py orbitals. So here's my positive on this one. Here's my negative, and here's my negative on this one. And so this is a py orbital. All right, we can add those two together, and what do we get? Well, the positive parts on top add up to make a bigger positive part on top, right? Like that. The negative parts on the bottom add up to make a bigger negative part on the bottom, like that. So 2p orbital, they come together to form a molecular orbital. We need to give this molecular orbital a symbol. What's the Greek symbol for p? It's pi. So we call this a pi orbital. And because the electrons here seem to hold the two atoms together, we'll call this bonding. So that's a pi bonding orbital. We'll repeat the same process, except now we're going to subtract, right? So I'm going to draw back my orbitals. There's my positive and positive parts, my negative and negative parts, but I'm going to subtract now. There's my two nucleus. Well, what do we think happens in this case? Very similar to what happens for the s orbitals. The top parts, if we're subtracting them exactly in the middle where they get subtracted, they completely disappear. And then there's going to be a little bit of the positive left over here, and then a little bit of a negative left over here because we're subtracting, right? The second one has to change sign. And similarly on the bottom, there'll be a little bit of negative left over here, and a little bit of positive left over here. So this is another py, two py's, right? And this we'll call pi star or antibonding. A very similar thing, the pz plus pz orbitals are basically the same as py plus py, right? You can imagine it. Remember, the pz just runs in and out of the page, and so you can imagine it doing the same thing. It will form one pi and one pi star orbital. So let's look at the px case, right? So here's my nucleus. There's my nucleus. Let's space them out a little bit more. For px, right, here's the positive part. Same for this atom. Here's the negative part. So these are px orbitals, both of them. And we're going to add them together. Well, what would happen in this case? In this case, right, the positive and negative right in the middle here will perfectly cancel each other out, but there will be a little bit of negative left over there and a little bit of positive left over there. And then the ones on the outside really wouldn't get affected at all, right? They'll just remain exactly how they are. I'll come back to naming that one in a second, but let's draw the other situation. we have the 2px, positive, positive, negative, negative, but this time we want to subtract them, right? So again, these are all px orbitals. We want to subtract them. Well, what happens when we subtract them? In the middle here, remember when basically subtracting just means changing the sign. So these two signs will flip. This part will be negative and this is also negative. So where they meet in the middle, they actually just form a bigger negative part in the middle, kind of like that, right? And then on the outsides, there's a little positive part and there's a little positive part. Remember, these negative and positive signs that I'm using are just arbitrary. You can flip the signs and it'll be exactly the same thing. All right, so how do we name this? Well, it looks nothing like these orbitals up here for the pi bonding and pi anti-bonding. In fact, the second one looks very much like this sigma bonding right here, right? This one on the bottom here looks very much like that, just the sign is different. So they actually call this one a sigma bonding as well, because it looks like a sigma bonding, which means that the one on top we'll just call a sigma star or anti-bonding. Everybody with me so far? All right. So if we were to draw these in a diagram, usually we draw them in a diagram here with energy because it's nice to see sort of what their energies are. And let's say at the two ends, this end here and this end here, we're going to look at the atomic orbitals. And for atomic orbitals, we know that, there's a 1s, then there's a 2s in energy, and then there's a 2p in energy, and so on and so forth. And so similarly on the other side, there's going to be a 1s, a 2s, and 2p, and then we can go higher and higher. Well, when these come together, the 1s will come together to form two different orbitals. Think of this as like however many orbitals you put in, that's how much orbitals you need to get out. So you have a 1s orbital on the left, a 1s orbital on the right. You combine them together, you get two orbitals. And we said that when we mix s orbitals together, we get a sigma and a sigma star. The bonding without the star is always going to be lower in energy than the anti-bonding, which is always going to be higher in energy. So sometimes you see little lines just showing you to show you that. So one is always going to be lower in energy than the 1s you started with. One is always going to be higher in energy. Same for the 2s, right? You can form a sigma here and a sigma star right there. For the p orbitals, I'm going to erase this and draw them a little bit higher because we need more space. So that's 2p, and this is 2p. They form 4 different pi orbitals and 2 different sigma orbitals, as we just seen, right? But their exact order can change. But I'm just going to show you one situation where maybe the lowest one here is a sigma. Then you have 2 of the pi's. Then maybe the 2 pi star. And then the sigma star up here. The orders of these can change. So orders can change depending on the molecule. But for now, let's just stick with this order. This diagram here is often called a, so these are your molecular orbitals in the middle where the AOs come together. This is often called a molecular orbital diagram. And it just gives you a way to like combine atomic orbitals and try to see where they land in terms of energy and stuff like that. So whenever you see things like 1s, 2s, 2p, think atomic orbitals, and those are only really associated with a single atom. If you're thinking about a whole molecule, you should think sigma orbitals, sigma star orbitals, pi star orbitals. That's the language you need to use for molecular orbitals. And then just like how you would fill a atomic orbitals with electrons, you would fill molecular orbitals with electrons, starting with, for example, the lowest first and moving your way upwards. Any questions on this so far? I know it's a lot to take in a very short period of time, but I also do know that I go over this with my Gen Chem students, so hopefully it seems somewhat familiar and you can pick it up much easier. All right, so one more thing I want to add to this discussion, which is the idea of a bond order. So a bond order, usually given the symbol N, would be the number of electrons in all of the bonding orbitals minus all of the electrons in the anti-bonding orbitals divided by 2. These are number of electrons in each of those. That's the bond order. And you can think of this as representing the number of bonds. But they can tell us more than just number of bonds, right? The bond order N can also tell us about bond lengths, right? Basically, higher N, meaning you have more bonds, mean shorter bonds. The more bonds you have, the shorter they're going to be. Also, higher N means stronger bonds. The more bonds you have, the stronger they're going to be. And this method also allows for things like fractional bonds. You could have a half of a bond, right? Whereas in organic chemistry and stuff, I'm not going to speak for them, but I was going to say that maybe you can't have half a bond in organic chemistry, but maybe you can, who knows? All right, so we're going to put all of this together and we're going to examine something simple to try to figure out if we can sort of understand what's going on there. So I see some people still writing, maybe. Okay. So let's do this. Let's use molecular orbital diagrams to figure out, let's figure out a few things. The bond order, the HOMO and LUMO orbitals, basically draw them. And what else? The bond order and yeah, let's just stick with those two. Oh, okay. And which bond is stronger? For let's do lithium and lithium, lithium bonded to lithium, or let's do lithium bonded to lithium plus. Why not? So I'm gonna do the first one for you. Actually, let's change the second one. What's the atom after lithium? Lithium, beryllium. Let's do beryllium bonded to beryllium. So I'm gonna do lithium bonded to lithium, and you're gonna do beryllium bonded to beryllium, just to make sure that we get, we understand all of this. So in lithium, we usually have a 1s and a 2s. So this is for lithium. The 1s would have 2 electrons and the 2s would have 1 electrons, right? Lithium has 3 electrons in it. So lithium bonded to lithium, we need to sort of, I'm just going to draw half of the diagram. But we need to figure out sort of all of the molecular orbitals that make up this molecule. And because we're only dealing with the 1s and the 2s electrons, I'm only going to look for the sigma star, and then the sigma and the sigma star here again. Right? Now, lithium 2, or lithium bonded to lithium, has 6 electrons. So I need to fill this with 6 electrons. 1, 2, 3, 4, 5, 6. Right? Okay. So that's the molecular orbital diagram. What's the bond order? The bond order is the number of electrons in the bonding orbital. So this is our bonding, and this is our bonding. Remember? Bonding, bonding. The stars mean anti-bonding. So there are 1, 2, 3, 4 electrons in bonding orbitals. There are 2 electrons in anti-bonding orbitals. So the bond order is 1. Basically, a lithium-lithium molecule has a single bond. All right.
So does Hund's rule not apply here?
Hund's rule only applies when there's degenerate orbital energies. In this
Okay.
case, for the S's or the sigma orbitals, they all have very different energies, so it's easy to figure
Since
that one out.
they're not degenerate. Okay. Thank you.
Yeah, they're not degenerate. All right, so we got that bond order as 1. The other thing that I wanted us to do is draw the HOMO and LUMO orbitals. Well, we know that this one's the HOMO, and this one's the LUMO. And we learned about how to draw those, right? So a sigma orbital, if you remember what it looks like, a sigma orbital looks something like this, where in the middle, one big blob like that, if you remember, sigma orbital for 2 s orbitals coming together. So this is the HOMO. For the LUMO, it's a sigma star. So if you remember what that looks like, there's going to be a little bit of positive over here and a little bit of negative over here. The easiest way to sort of remember what these look like is to just look at these pictures. The sigma has like one blob. The sigma star multiplies that by 2. So there's 2 blobs. The pi has 2 blobs. And so the pi star is 4 blobs, right? Multiply that by 2. As you probably will be able to guess, a delta orbital, right? A d orbitals, when they combine together, will have 4 blobs, and a delta star will have 8 blobs. But I don't think in any exam you'll work with d orbitals for these molecular orbitals. So that's for lithium 2. I want you to do the same thing for beryllium 2, beryllium bonded to beryllium. And just spend some time coming up with the bond order and the HOMO and LUMO orbitals. It might be a little bit difficult to figure out the LUMO orbital. But your best guess would be good enough. And once you have the bond order calculated, just type it in chat so that I know that we're ready to move on. But I just wanted to get you to get some practice doing this. All right, we got one answer so far. So yeah, a couple of people replied. They got 0 for the bond order, which is correct. So if using this sort of picture, a lithium 2 molecule, so Li2, will have a single bond, but a beryllium 2 molecule will have no bonds, right? Which means that obviously the lithium will have a stronger bond than the beryllium because the beryllium doesn't have any bonds there. And hopefully you're able to draw at least the HOMO orbital. For beryllium 2, the HOMO orbital looks like the LUMO orbital for lithium 2, in case you're wondering. The LUMO orbital might look very different though. The LUMO orbital, depending on what orbital comes higher, which in this case we didn't draw, could be another sigma orbital or could be a pi orbital or whatever. The LUMO orbital will look different. All right, so hopefully that gives you just a little bit of understanding of how we can put atoms together to form molecules and what those wave functions look like using this picture of a linear combination of atomic orbitals. Now it's not perfect because we're making a lot of assumptions, and I don't think beryllium 2 has 0 bonds. I'm not an expert on that. It might have a very, very, very weak bond. I know the example of helium 2. If you use the same picture, the bond order for helium 2 is 0. But people have done experiments and helium 2 as a molecule exists, right? The bond order is not 0. There is a bond there, even though it's a very, very, very weak bond. There is a bond for helium 2. So this picture is good to understand some things, but it's not perfect. And so that will bring us to the end of this chapter. And basically everything from up to here is fair game for the exam. I wanted to ask you before I move on to other stuff, if there's any questions about that or anything else that we've done in this chapter that you would like to ask.
What can we expect as far as free response?
What can you expect in terms of what, sorry?
Free response questions or essay questions.
Essay type questions, free response, that's what you said. So what do we look at this semester? Let's see. We talked about spin and how you might want to include spin in the molecular orbital. The previous chapter, we talked about harmonic oscillators and why harmonic oscillators are not necessarily perfect for describing vibrations, right? We talked about how the Morse potential is better. We looked at what else? We looked at the Pauli principle, right? That's another free response type of problem where, um, you know, are you able to explain Pauli principle in its most simple form or general form, as well as the more common form that you know it in chemistry, and how those two things are essentially the same? You know, what are fermions and bosons? Born-Oppenheimer approximation. We talked about the Born-Oppenheimer approximation. So can you describe what it is and how it works and why we make it? Yeah, I think those are all. That's a very difficult question because I wrote the exam a couple days ago now, and I'm trying to remember all the things. And if I tell you too many things, you'll probably know, oh, that's exactly what's going to come on the exam, which is fine. If you want to know those things, pretty much all the things I've just said are going to be in the exam, in case you're wondering. So yeah, other than that, it's just solve some simple problems based off of the ideas that we did over the past couple of chapters.
Will the rigid rotor stuff be on this exam, or was that the
Rigid.
last?
I'm trying to think what we covered last, up to the last exam. So harmonic oscillators. I'm looking through the exam. Yeah. So particle in on a ring and particle on a sphere. So basically the topics that you should be thinking of is that would be covered would be the harmonic oscillator, the rigid rotor, or as some people call it, particle in a ring, particle on a sphere, the hydrogen atom, and then electron spin and the helium atom stuff that we did in this chapter. It's a lot of things, but I promise you, I mean, the last time I said this and it wasn't true. I feel like the exam's easier than the last one. So yeah.
Quick question. With this exam, kind of like how with the last exam we had some, like, I guess, real application questions with that were the more challenging one, and then with the simpler, like just the system that's been set up for us. On this exam, will there be something similar, or will it just be one or the other?
No, I didn't go in crazy with any of the problems. Like none of them are. The only real system applications that I have here are, can you calculate energies of things in like joules, or can you calculate angular momentum of things given different values, you know, things like that. Not like, here is a long molecule, calculate the energy difference for it, if that's what you were talking about, you meant by real. No, there's none of those, because I learned my lesson. I don't know if you've learned yours, but somehow people don't like those questions. I don't know, even though that's the like real life application of these quantum mechanical problems. But no, I don't have any of those specific ones. I just have, here's some numbers, give me an energy or whatever. Any other questions? All right, if you think of them, let me know. That's what I'm here for. I will try to remember to copy all of my notes this afternoon when I get to campus, scan them all in and send them to you. And apart from the end of chapter problems that I sent, going over the problems that we did in class and just reading your notes. I have no idea how you guys study, but just like reading your notes over and going over those practice problems would be a good way to study. All right, so with that, if you don't have any more questions, let us finally talk about spectroscopy. So you're gonna have to learn this stuff and then put it out of your brain for the exam, and then put it back in your brain for the final exam. It's gonna be hell, but we're gonna make it work. So the whole point of quantum mechanics is to make you understand how matter behave at the smallest levels, atoms, molecules, and stuff. And the only way we can understand how molecules behave at those levels is to perform spectroscopic experiments on them, right? We can't see atoms and molecules with our bare eyes, right? So we need all these fancy equipment. And so to really see the quantum mechanical effects in action in real life is to use spectroscopy. So I know we don't have a lot of time because we have the rest of today, and then Thursday is an exam, and then there's 2 lectures before the semester is over. So I'm gonna try to cover the important parts of chapters, I think 13 and 14, or 14 and 15, just the important parts. So all I want us to do as we talk about spectroscopy is to learn about the properties of light, and how it may interact with matter. And I'm gonna just talk about 3 kinds of spectroscopies. So we're gonna learn about the origins of rotational, vibrational, and electronic spectroscopies. There are many other types of spectroscopies, but we're not really going to focus on those. I'm going to try to keep this pretty straightforward. And I'm sure you've had some experience with at least 2 of 3 of these. And during the course of their like undergraduate degree. Vibrational, for example, many of you did IR spectrum. That's vibrational. Many of you did, I know you all did UV vis spectrum, because we do that in Gen Chem, right? With the SpectraVis and probably with a UV vis spectrometer. I don't know if you've done any rotational spectrum, but that's also part of IR and microwave region. Microwave. So I feel like you've had some experience with these, so we're gonna focus on those. There are other types of spectroscopy that you probably did have experience with, but unless you really want to talk about those, we're not going to. So let's start with the basics of spectroscopy, which is sort of light. So I'm going to call this little section light matter interactions. And if you haven't guessed by now, spectroscopy, right, is the study of the interaction of light or electromagnetic radiation or light with matter. So to understand spectroscopy, we need to understand light and we need to understand matter and how they could interact. Now we spent 95% of the whole course so far trying to understand matter, right? Electrons and molecules and how they behave according to quantum mechanics. In the very, very beginning, we also talked a little bit about properties of light, how light can exist as a photons and stuff like that. And so now we're going to try to make those 2 things work together. And them working together is what leads to spectroscopy. So to understand how they could work together, let's look at some of the properties of light that is important for spectroscopy, right? There are many more properties of light than the ones we're going to talk about, but these are the ones that are going to be important for spectroscopy, and these are the ones that we're going to come back to every time. So the first one is a photon of light has an energy. We talked about this, right? The energy of a photon is Planck's constant times the frequency, E is equal to h mu. So we have to remember that. Photon of light has an energy. The second property of light is that we need to keep in mind is a photon of light has a spin. and therefore an angular momentum. I mentioned this earlier, right? Does anybody remember what the spin of a photon is? Electron has a spin of a half.
Is it 1?
Yeah, a photon is a boson, has a spin of one. So if it has a spin of a one, it has a spin, it means it has a angular momentum, which is s into s plus 1 square root of s into s plus 1 times h bar, right? That's the spin angular momentum. It also has a z component of that spin, which because s is 1, the z component could be 0 or plus or minus 1. So it's 0 or plus or minus 1 times h bar. So I'll put the h bar back. And this is the z component of the spin. So photons have energy, photons have angular momentum. And then the third thing that I want us to focus on, the third property of light, is that light is an oscillating field. So an electromagnetic field, an EM field, is oscillating. Right? So let's say we have light moving in this direction. I'm going to use green for electric field. So maybe this is the electric field. That's the electric field. At some point it's positive, at other points it's negative, right? That's what this little thing says. And it oscillates between positive and negative over and over again. And then you might have the magnetic field part running perpendicular to that. It's hard to draw, but imagine this is going in and out of the page, right? So that's the magnetic field. Let's call it B. I'm not going to tell you why we call it B, but B is the magnetic field. Because I don't know why they call it B. I was going to put M, but let's use B. So it has an oscillating electric field and a magnetic field, oscillating magnetic field, right? So if you imagine light has this field that's moving up and down, up and down, up and down. When it interacts with matter, I'm going to save that for a second. But those are the three properties that we have to focus on for light. So when light interacts with matter, these properties don't just disappear, they have to go somewhere, right? The first one is the energy. The energy has to go somewhere because energy must be conserved. Energy doesn't just poof disappear. The second one is angular momentum. Light has an angular momentum. So when light interacts with matter, the angular momentum must go somewhere because angular momentum must be conserved. And then the third is this electromagnetic field. When it interacts with matter, it has to go somewhere. So that also plays a part in this whole light matter interactions. So if you think about it, let's just draw some picture. Let's say this x-axis is my time. Let's say we have a light ray coming in and I don't know, a piece of matter coming and they interact with each other and then the light gets absorbed. So this would be for absorption, right? This is the point where they interact. If you add up the energies before, so the energy of the photon plus the energy of the molecule before interaction should be the energy of the molecule after interaction. That's just conservation of energy. The angular momentum of the photon, I'm using L for angular momentum, plus the angular momentum of the molecule before interaction should be the angular momentum of the molecule after interaction, right? That's just conservation of angular momentum. So let me just write that right here. Both energy, lost somebody, and angular momentum must be conserved. that's just good business, right? You can't just have the energy or angular momentum go disappearing. On the other hand, if you have the opposite situation where you're trying to emit a photon, so in emission, let's say this is our time axis, right? And you have a photon just minding its own business, going about its business, and all of a sudden, poof, a photon comes off of it. And then the piece of matter molecule does something else. It's the same idea. The energy of the photon, but the energy of the molecule, sorry, before emission should be the energy of the molecule plus the energy of the photon afterwards. And similarly, the angular momentum of the molecule should be the angular momentum of the molecule plus the angular momentum of the photon. Those things must go somewhere. By the way, these diagrams that I'm drawing, they're called Feynman diagrams, and I can't spell Feynman, I think. And they're much more complex than I'm showing you here. I'm just showing you for like an electron or a piece of molecule interacting with light. The squiggly line is light, and the solid line is a molecule. All right, so those are the first two properties, energy and angular momentum, and we learned that they must be conserved for this whole thing to work. The third situation is this oscillating electric field, right? And the whole oscillating electric field idea means that if you think about it, the field is going back and forth. When that interacts with the molecule should also take on that sort of going back and forth, right? So we call that the oscillating fields lead to what we call a frequency matching condition. All that means is that this going back and forth with the electric and magnetic field, somehow that property must be transferred into the molecule if it's absorbed, or emitted from the molecule if the photon is emitted. So how do we keep track of that? How do we know whether the molecule absorbs this oscillating field? Well, that is actually reflected in the intensity of the spectrum. And ask me questions because this is all very different from what we've done so far. So please ask questions if anything seems confusing. But the intensity of the light in a spectrum is proportional to something that we call the square of the transition dipole moment. So m is the transition dipole moment. Well, sorry, there we go. And I here would be the intensity of the spectrum, or the probability to absorb or emit a photon. We know that probabilities are usually related to things square, right? And here's another probability. There's so many probabilities in quantum. Why is it a probability? Well, if you have a photon, one photon, and one molecule, and they pass by right each other, it doesn't mean that that molecule would absorb that photon with 100% or 0% for that matter. There's always going to be some probability of that photon being absorbed and some probability that it's not. That probability is related to the square of this transition dipole moment. This transition dipole moment, m, is actually written this way. So let's say this is some final state. This is the dipole moment operator. This is some initial state integrated over all space. So that there is the dipole moment operator. Written in Dirac notation, this whole integral, we can just simplify it to look like this. Final, the dipole moment, initial. Why initial and final? Well, if you're absorbing a photon, things must change, right? You can't absorb a photon and be the same in the end as you did in the beginning, right? Something must change. So there has to be two different states here. Some initial state, you absorb the photon, and then some final state. And to figure out whether that will happen, we use this transition dipole operator, and then you square that, and that will give you the probability that this transition is going to happen. For those of you wondering, this dipole operator takes into consideration all of the charges in the system. It's the charge times the x operator plus, times the x position of the charge, the y position of that charge. I keep writing b. And the z position. So these are all x, y, and z position operators of the same charge. So remember, a dipole is a charge times a distance. So basically, the dipole operator just sums that over for every single charged particle in your system. That's your dipole.
Could you scroll up a little bit?
Sure.
Thank you.
So this here sort of gives you the probability of a photon being admitted and the probability of a molecule will go from one state to another state, right? So those are our three conditions. If you want a spectrum to happen, or if you want the light to absorb, the energy must match, right? Because the conservation of energy. The angular momentum must also be conserved. And also the dipole moment operator must be non-zero. Because if the dipole operator is zero, if this transition dipole is zero, then basically this m squared will be equal to zero, and we can't see the transition using spectroscopy. Basically, that photon will never be absorbed or will not be absorbed. Everybody with me? All right. So we have three properties of light with three different conditions for determining whether or not that light will interact with matter. And that whole relationship is what determines spectroscopy. Now, I mentioned that when you observe a photon, something must change. I mean, yes, the energy must change, the angular momentum must change, there's this frequency matching condition. This whole process involves change, always involves change, right? If nothing was changing, then you can't see anything, right? And so when we think about change, we should think about motion. That's what change is, motion. Something is moving somewhere. So as we're doing this, we need to think, what are the different motions inside of an atom or a molecule, right? Because those motions need to couple with the light that's coming in for this whole thing to happen. So what are the various types of motion in a molecular atom? And I see a couple of people writing. So I'll pause here for a second for you to think maybe what are different kinds of motion that a molecule can undergo. And I'm sure based off of the kinds of problems we solved, you can guess what some of those motions are going to be, right? So what are the various motions of an atom or molecule? Because that will determine the kinds of spectroscopy. Well, the most basic motion is just translational motion. You have a molecule here, it can move over here or over here or over here or back here. It's just moving, right? That's translational motion. So we call this one molecular translation. Basically, movement from place to place. When you think about a molecule moving from point A to point B, it doesn't require much energy, right? So this is very low energy. And you can do this. If you have a molecule moving in this direction, you can bring a light in and change the direction slightly and that sort of thing. But, we're not really interested in that. We're not really going to be interested in translational motion. But I just wanted to point out that that is a possibility. Two, there's molecular rotation. A molecule could rotate, right? Spin in space. This has reasonable, it's small amount of energy. It doesn't cause much energy for a molecule to rotate, but it's more than translation in most cases. And so this happens in the microwave region of the spectrum. If you want to change the rotation speed or the rotation energy of a molecule, you need to add microwave electromagnetic radiation to change that rotational speed. Is this related to how we heat foods in microwaves? Yes, yes it is. The third kind of motion that we might expect is vibrational motion. So molecular vibration. And these are all the different molecules of the atom vibrating, shaking, trembling, however you want to think about it. And this happens in the infrared region of the electromagnetic spectrum. Another kind of motion that might happen in a molecule is the electron could change energy levels, right? The electron could change energy levels, and we call that an electronic transition. And this happens in the UV or visible region, depending on the specific molecule.
What happens if you go above UV, like into X-ray and gamma ray?
So you can. So for UV is what you need to change an electron from one energy level to another energy level. As you go deeper and deeper into the UV spectrum, closer to X-ray, it becomes what we call ionizing. Meaning it's so much energy that not only are you changing the electron orbital from one lower energy to a higher energy, but it's so much energy that that electron gets ripped away from the atom. So as you get closer to X-rays and gamma rays, it becomes ionizing. You start to rip electrons away from the atom,
Okay.
which is in itself a good way to probe matter and see what it's made of. Another thing that X-rays are good for is determining spacings between atoms for crystals, for example, crystal structures, because the wavelength for the X-rays match the wavelength for the atomic distances, and so you can find distance between atoms. And then you can also like probe the proton with like X-rays and gamma rays, but we're not going to go there. We're going to stick to these. But there are other things, like you mentioned, there are other things that you can learn about. So let's say the electron could change spin. That's another change that could happen. We know that electrons have a spin, alpha or beta, and you could change that spin. When you do so, the type of spectroscopy here is called electron paramagnetic resonance, or EPR, or electron spin resonance, or ESR. So the types of spectroscopies where you only focus on changing the spin of the electron from one spin to the other. There's also a type of spectroscopy where you change the nuclear spin. Could change. This one you're probably familiar with. If you're changing nuclear spin, that's called nuclear magnetic resonance, or NMR, which some of you might have done. Those have very different energies though. We're going to focus on these 3 or 4 types, really these 3 types. And as we order them here for at least these 4, right, you can probably tell that we go from low energy There we go. To high energy. And we could go even higher energy, it becomes ionizing at that point. In fact, I'll say this right now. If you calculate an energy change from some initial energy level to infinity, that's ionization. How do I spell it? Ionization. That's how you calculate the ionization energy for any atom or molecule. What happens if the electron goes from some initial energy level n to the final energy level being infinity? Whatever energy that comes out to be, that's the amount of energy you need to rip that electron away from the atom. Does that make sense? Cool. That's the ionization energy. All right, so we have three properties of light. Energy, so conservation of energy must play an important part. Angular momentum, so conservation of angular momentum must play an important part. And then there's this dipole moment operator thing that tells us the intensity. Then we looked at the various motions of atoms and molecules. Atoms could translate, they could rotate, they could vibrate, the electrons could change energy levels. And those are all going to lead to various kinds of spectroscopy. So what we're going to do over the next couple of lectures is figure out how each of those fit in with light. So how does a molecule rotating interact with the properties of light that we talked about? How does a molecule vibrating interact with the properties of light? And hopefully by the end, you'll get a clear picture of how we can come up with these vibrationals or these different spectrum that you might have seen over your course here. Any questions about any of those? No. So the next time we meet, we're going to talk about molecular rotation, then following that, molecular vibration, and so on and so forth. I'll try to get you my notes for the past couple of chapters scanned this afternoon. And if you have any questions about the exam, let me know and I'll try to answer them. All right, enjoy the rest of your day. I'll have this video posted soon.